repulsive, if I may say so, but 10 minus 6, 1 millionth of magnetic field you apply to is repelled by yourself. And this is what essentially happened. The reason why the water is not on the floor, because the magnet creates out of the water a little bit anti-magnet, and they compensate gravity. It's a long story why it's stable. It's we published quite a good scientific papers about stability of the water, but compensation of the gravity is a trivial fact in terms of science. But then next morning I come to the lab and say, you know, water levitates in my magnets, and no one believes me. All my colleagues, many of those who were routinely doing this research in high magnetic fields for 50 years until close to retirement, they say, okay, you joke, it's a hoax, what you're telling us. So I have to show them water levitating. They came with brilliant ideas, what else can be put inside, and everything we put inside levitated, except, of course, some special materials like iron, nickel, and so on, which are strongly magnetic, which we call ferromagnets. So yeah, it was surprise. The biggest surprise was that my colleagues were not aware about this, and looking through the literature, we found out that no one has done this duffest thing to do. So, and then how to demonstrate it to the public, to you. One way, water demonstrate, another way to prove it, to put something live. Unfortunately, my face didn't fit into the magnet, so otherwise you would be seeing my myself levitating in this magnet. But we put a little frog and make this kind of movie with the frog, and then it hits the media, and if frogs can levitate, then everything can levitate. So the result of a very simple question, very simple experiment, then a lot of demonstration to the colleagues who came all over the world to see that it's not a hoax. People claim that this picture was kind of made up by, it was 30 years ago, no artificial intelligence, no Adobe Acrobat to do this, but that I made up this picture by projection. So I had to show those. That was the big work. Very simple, very little money involved. That it turns out to be in many textbooks these days. And one of the best compliments I ever get is when you're walking in a big conference. A guy came to me, 10,000 people, American, whatever, physical society came around. Guy came to me in the corridor. I know you. I rolled my eyes. Okay. Another fan of graphene. And he tells me, you know, I have no idea what graphene is, but your frog. And that's kind of heartwarming, because he explains to me that he shows this picture to his students at the university at the beginning of the lecture on magnetism, and attention is taken. They want to understand how live creatures can levitate and so on. But probably the best outcome of this story for this experiment, I got the Ig Nobel Prize, which is kind of parody prize for to the Nobel Prize, together with a theorist who was actually much more famous as who was nearly as famous as I am now, Sir Michael Berry. Berry, maybe he will get Nobel Prize one day for sure, But uh, he was kind of writing theory about stability and so on. But in addition to this prize, I mostly value this letter, which came, nearly 30 years ago, 25 years ago, 1997. It's from a girl from Alaska who wrote to me, I'm interested in how you got the frog to float. I'm 9 years old and I want to become a scientist. So I rest my case with this kind of letter. I think the experiment was worth it. Let me give you the whole idea how at least I try to work. When you do this kind of curiosity experiment, you often come with other ideas. What else? I have done quite a few different experiments in different areas, and this is another one which you might consider to be successful. That's another very far from my area of research. Actually, at the time of doing research, I don't think I might not have seen a real gecko. Don't remember actually, but that's gecko climbing the walls, and the question is, how do they do that? Before me, people did answer a bit how it works, and the reason is those toes of geckos which are covered with a dense forest of hairs, like your hairs, but much more thin and much more dense. If you pull out one of your hairs and touch any surface, there would be interaction between this hair and the surface, and this is called van der Waals interaction. So all those surfaces, whatever you put together, its atoms essentially try to stick together. So this is quite minute force. It's nanonewtons. You wouldn't notice it if you use it by hand. To measure this kind of forces, you need atomic force microscopy and this kind of facilities. But what Gecko did, they grow billions of hairs there, and when you get 1 nanonewton, 1 billions, multiplied by billions of hairs, and they learn how to use all those hairs at the same time. It creates quite a formidable force of about 1 Newton, 10 newtons. It's enough to keep geckos on the wall. It's dry adhesive. It doesn't use any glue or any hooks like some other animals use, like spiders. In this case, it's pure physics mechanism of interaction between different molecules. So the idea maybe was uh, very simple question. Okay, that's the same scale. I'm doing my very fundamental research in the lab, but that's I have the facilities to reproduce this. Can I do this? And what would happen if I try to mimic those hairs? So about 20 years ago, we make this dense forest of hairs, and the original idea of mine, because I knew how it's important to get sort of an appeal, was to make a gecko glove and give it to my students and let them out of a window and see what would happen. But unfortunately not for the lack of students, but for the lack of material that's reasonably sophisticated, even especially at those days 20 years ago, to make these hairs on scale. We make only a very small patch for demonstration, 1 centimeter around, and all I could possibly do without spending a fortune is to demonstrate that it's indeed work and so on. So the result of this research, which maybe was done on a few $1,000s altogether, and in my spare time, rather than funded by taxpayers and so on a big grants, I was still doing some kind of fundamental research at that time, was that a new small subfield appears, which is called dry adhesives. There are many people working in this field. The paper is extremely well cited, and people, 10 years later, I was invited into a lab where a person was demonstrated me a Gecko glove. He was hanging, a big guy, bigger than me, was hanging from the ceiling like the Spider-Man, and the problem is why we don't have Gecko gloves. They, whatever we do, those hairs clamp. And after few attachments, actually, 2, 3 attachments, all adhesion disappears. So how geckos reproducibly clean their hairs, make them standing like this rather than being clamped to the surface to each other, we don't know. That's what people investigate. Maybe one day you will see Gecko gloves, maybe not. I don't know. My finite example of what curiosity brings to is another random idea. Came 20 years ago, and the question was how thin you can make graphite. Those ideas seems to be random, but in fact they come from background knowledge. So no knowledge is useless, whether even if you study Greek or Asian philosophy, and maybe or maybe not, I don't remember now, the idea was essentially the same, at least with benefit of hindsight, that which ancient Greeks had. Anyone knows where the word atom came from? No one. I guess it's someone knows. Okay, don't be shy. So essentially, it comes. You can check it on Wikipedia. I might be wrong, but some people already checking. I see. But I think it was one of Greek philosophers. I don't remember Socrates or whoever in his school make a Gedanken experiment, thought experiment, and they say, let's take a stone, and yeah, you're welcome to correct me if I'm wrong. Okay, I would be curious. Who was the philosopher? Okay, you'll tell me while I'm telling the story.
Uncuttable, indivisible, uncuttable.
What philosopher?
I think, I didn't know the name, but the Greek word means, the atomos means uncuttable.
Yeah, that's this I knew, but I didn't know. Yeah, indivisible essentially atom means. So the Gedanken experiment, the German word Gedanken means thought experiment. So the thought experiment was you take a stone and divide it into two. Then half stone divided into two, quarter divided into two, and two, 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 and continue divide into smaller and smaller pieces. And then, as usually Greek philosophers did, they speculated that at certain moment you can't divide it anymore, and this is the smallest piece they called atom, indivisible, or whatever. Which philosopher did you find?
Democritus
Oh,
and Leucippus. So these two, Leucippus, I cannot pronounce it properly. Leucippus.
Democritus.
His teacher, inspired by.
Yeah, Leucippus, I don't know. By Democritus is well-known philosopher. Yeah. So, okay, something I learned today for my future talks. So the same we know. Mica. Everyone knows what mica is. You know, this insulator, which is splits very easily into planes. I don't know. When I was a child, there was a lot of mica insulation for irons or something like that. Okay, you can find easy these days as well. Mica. It's a natural mineral. It's very easily got into thinner and thinner pieces. But scientifically, for me, was much more interesting to deal with graphite. Graphite is a very soft material, and it also can be divided into pieces. So the question was how thin you can make this graphite. So following Democritus question, but 3,000 years later, we decided to do this experiment. I had a Chinese student at that time. I think he was my first Chinese student at that time, Zhang Da. He's now a professor somewhere in Shanghai, and it was his PhD project to make graphite as thin as possible. We did all sorts of things using modern machinery, including tiny polishing machines and so on. Yeah, spent maybe not a whole year, but half a year at least trying to thin graphite into thinner pieces. Nothing worked, and eventually a very simple technique we came around. It's very well-known technique for probably at least 50 years before me, and maybe 150 years, and using widely in scientific community. And the technique is you want to study graphite, and graphite covered with all sort of rubbish when you get it. So people clean the surface of graphite. They put scotch tape, sticky tape, sellotape, whatever you call it, on the surface, peel it off, and study the surface. Pristine, very clean surface of graphite. Hundreds and hundreds of papers, thousands of papers about graphite surfaces, how good it is. It's not in this community, but if you talk at the university, there would be people who were doing this routinely using AFM or STM microscopy, which are kind of characterization technique. And people forget they studied graphite and they forget about what is on this tape. So looking for how thin graphite can be, we look in the microscope. Very simple experiment. You can do it at school. It can be a good project to find for you a few layer graphene. That's what you see. Take this tape. The tape is several times, make thinner and thinner, divide it into two. As you see those pieces, there was one piece, then it was divided into two, then there was 4 times thinner piece, and that's a little bit continued. And then we looked at the microscope. And what you see here, black. The light goes through, can't go through, because it's metal. Graphite is a metal. It's doesn't metals do not allow light through. But you see some pieces like this one over here. They are, or over here, they are transparent. That tells you that this material is very thin. Only very thin metal can be transparent. And this was a eureka moment for me and for my students. At that time, someone else, another student, took over this project, but doesn't matter. It was, I have something which people didn't study before. Very thin, in this case, it's probably 5, 6 layers of carbon. It's 1 nanometer. It's 1 billionth of a meter, 1 millionth of the thickness of your hair, and so on. Very thin fields. A new experimental object where no man has been before. So, eureka. On one hand, okay, very thin object, but it's apparently junk on the surface. And I told me many people had this junk and throw this junk away. Why someone would be interested in studying a junk? But as they say, man's rubbish is other man's gold. For me, it was not a junk, it was gold, because with my education, I knew how difficult it is to make thin materials. We live in three-dimensional world. All materials around us has height, length, width. That's the basic law of our universe. In our three-dimensional universe, you can't grow anything which would be flat, either lines of atoms or planes of atoms. It's forbidden by nature. The reason for this is temperature, because to merge atoms together, you need temperature, and temperature causes vibrations, and those vibrations makes flat structures or line structures unstable. So there are fundamental rules which forbid growth on those materials. But what we effectively did, and this is kind of retrospective thinking, I didn't think that way. It's only explanation what happened, why we were overwhelmed eventually with benefit of hindsight. When you grow a material in a allowed way, three-dimensional way, had three-dimensional material, we know they consist of atoms and molecules, and you can think like Democritus thought about, why wouldn't we extract as an atomic plane? Imagine very small tweezers and you pull out of one way Gedanken experiment. That's not forbidden, very important by any rules, because the material itself grown at its own melting temperature, no problems with that. But what we do, we extract plane at much lower temperature. In case of graphite, it's 10 times lower temperature, and this plane is not melted. So this is how, after tinkering with this sticky tape technique, you find a single layer. It looks visible to naked eye, despite it's only one atom thick. It absorbs 2.3% of light, which is a huge amount of light. Between me and you, there are billions of atoms, and we don't see them. Light goes through, and it's one layer of atoms absorbs 2.3% of light, and a very record amount of light actually is kind of absorbed. Probably the strongest absorbing material we know in this universe. So it still looks a little bit like rubbish, although it's 1 millimeter in size, but then you use modern techniques like transmission electron microscopy, and this is a real micrograph of carbon atoms, how they look like organizing a lattice. So we proved very quickly that it's a single layer, and this is a perfect crystal lattice without many or any defects, in fact. So if it were, it's nice. It's kind of refers to 3,000 years of history and so on, and it's nice to get to show that the materials could be single layer. It's really kind of would get a scientific impact that this kind of material exists, because don't make a mistake. You try this trick with most inert conventional materials, say take gold, for example, and evaporate gold. Gold is easy to evaporate as thin film, but and there are plenty of computer science side microchips, everything covered with a thin layer of gold. But then if you try to make this layer thinner and thinner at certain moment, you can't make it continuous. If you go below, say, 100 to 100 atoms thick, you evaporate this film and then put it vertically, and gravity make the film go down along the surface. This is those vibrations of atoms which I described before. They destroy the order. They force those atoms to clump into thicker structures. So only a few materials, not that few, but a combination about thousands, okay, few hundred materials we now know out of billions and billions of materials we otherwise know. Only a very tiny portion of those materials can exist at room temperature as one atom thick or one molecule thick material. So existence is the most special property, in my opinion, of this material. But if it would be only this, initially it's extremely simple structure and only carbon. You don't expect much. So the thickness, curiosity, and I would be not given this talk before if it would be the end of the, wouldn't be given talk today, because I wouldn't win the Nobel Prize for this. It's only existence, curiosity, good physics, good science, good crystallography, but nothing too so spectacular to impress the Nobel Committee. But having access to this material before other people did, because many people get interested, then we start studying properties of this material. And that's where real surprises came from. Of course, it's the thinnest imaginable material. You can't imagine anything thinner than one atom. That's my last slide. You don't need to leave now. It's the thinnest imaginable material. Because it's so thin, it has the largest surface area. What came as a surprise that this material is essentially stronger than diamond. It's a very strong bond, stronger than diamond bonds, and yeah, we don't know materials. It's stiffer than diamond. Diamond is very stiff, you know, you can't press it, but this material you still can stretch 20% and it doesn't break. A little bit like rubber. And then it's a lot of properties due to its structure, due to electrons which move through this material. And I skip this one, but actually just to make a point that the Nobel Prize was given probably for this line, this line, this line, and this line, for 4 lines out of many, many lines. And people like those superlatives of graphene, but probably the biggest surprise, which we realized with hindsight, was that the material is so different from its parent. Graphite, if you take a piece of something like Democritus thought that if you take a small piece of something, it would be still showing the properties of the big stone. But in fact, this derivative of three-dimensional material turned out to completely different from its parent and in many respects superior to its parent. Graphite is soft material, graphene strongest measurement. Graphite is the most chemically inert material. Graphene is chemically active. Graphite conducts electrons very badly. Graphene conducts electrons better than copper many thousand times, and so on. And that's what the Nobel Prize was given for, starting with a very simple question, 3,000 years old question, but curiosity and then hard work digging down into the properties bring us so many surprises. And these days, graphene is in industry, it's in many gadgets. If you have, for example, an electric car, you're a proud owner of graphene-based technology because somewhere in anodes of the car, they add graphene to those lithium-ion batteries, and it gives you an extra mileage, several percent, maybe up to 10%. It's a small improvement, but important improvement. And that's all started with very simple questions. The things get much more complicated afterwards. So with this one, I think I'll finish my presentation, which took me longer than I expected. And best of luck for all of you with asking questions, silly, sometimes sounding stupid questions. Don't be afraid to ask those. And we started from today. Thank you.
Thank you, Professor Geim, for a truly inspiring speech. I believe everyone has learned a lot. We will now begin a Q&A session. If you have any question, please raise your hand and turn on the microphone on your desk. The session will be hosted by Teacher Bryant, an English teacher from TFG.
You're not going to believe this. The one word I cannot get out of my head right now is frog. And then, of course, graphene. And finally, the magic number 42. Good morning, everyone. Guests, teachers, and dear students. I'm Brian, an English teacher here at Taipei First Girls High School. It is both a pleasure and an honor to be your host for today's Q&A session. Thank you guys all for coming. Thank you for joining us, and thank you for being part of this special event. Now, big shout out, excuse me, to all the participating students from different high schools across Taiwan. Big shout out to all our international participants from Japan. Make some noise. Singapore, Malaysia, Thailand, and Vietnam. Did I miss any country? Oh, Taiwan, yeah. Now, it's fantastic to have you guys here. But of course, we're deeply honored and beyond thrilled to welcome once again our guest of honor, the 2010 Nobel Laureate in Physics, Dr. Andre Geim. A big round of applause. Now, thank you, Dr. Geim, for your inspiring keynote and for your groundbreaking work on graphene. It's literally the thinnest material on the planet, and it's incredibly strong, and it's a great electric conductor. Your research, doctor, has transformed the way people understand physics, and it's also inspired young scientists all over the world, including students right here in this room. Now, fun fact, you already know this, but Dr. Geim is the only scientist in history to have received both a Nobel Prize and a Ig Nobel Prize. That is an interesting spin on the classic Nobel Prize. In Chinese, it's 搞笑诺贝尔奖. And that is a true testament to your creativity, humor, and boundless creativity, boundless curiosity in science. And so today is really a rare opportunity for us to hear directly from Dr. Geim in our Q&A session. So now we would love to open the floor to you, the audience. Now we have about 30 minutes for questions. So if you have ever wanted to ask a Nobel Prize winner something, this is your chance. Now don't worry if it's a simple question. Feel free to ask anything about science, research, life, or even music in the lab that Dr. Geim listens to for inspiration. So, before we get started, a quick reminder. Before you ask a question, say hi, introduce yourself, and then ask the question. All right, let me give you an example. Hi, Professor Geim, I'm Bryant, a student from Taipei First Girls High School in Taiwan. That's not quite possible. And here's my question. Then you ask the question, all right? Simple as that. Now, is everything clear? All right, if so, who would like to break the ice and ask the very first question? Raise your hand. All right, if I point to you, if you think it's you, then it's you. You don't have to look back, all right? So, go ahead. Turn on your mic and you can start speaking. Thank you.
Okay, so hello, Professor, and I'm Shen from Tainan Girls School. And I have a couple questions that I want to ask. So the first one is like about the graphene. Like you spread the graphite powder on the tab. Am I right? Like with the tab, you spread the powder on the graphite powder on it and then tab it. Am I right?
So it's a technical question how we make graphene with
Yes.
sticky tape. You can do many different ways. You can do with powder. You can do it with a chunk of graphite. In this case, it was chunk of graphite. Any material would do. You can even use your pencil trace, pencil, because pencil contains graphite, but it's very dirty material. Usually they put something else into pencils. Just take a clean powder or chunk of graphite, put it on sticky tape, scotch tape, sellotape would do it. Then bind this tape,
open it,
uncleave it, make it several times, making thinner and thinner, and then look in a microscope. So this is the real images, what you see there. You probably would have difficulties to get a single layer seed because the tape is a little bit dirty and doesn't get contrast. So it requires surface, but you will see a few layers very easily. Surprisingly, this technique, sticky tape technique, is used these days all over the world, including several places in Taiwan, because it's a very powerful technique to produce monolayers of material. People who don't use scotch tape, they use semiconductor kind of tapes, sticky tapes, which do not give much residue, but the technique essentially remains the same for 25 years. The best papers in science magazines comes from sticky tape technique.
Yeah, so my I want to ask is like, won't till the end the powder just step, like as the tab you have to fill it, right?
Yeah.
And won't it just step on the one side? Like you cannot open it and only the powder just step on one side because there's not much powder till the end because you always like flip it,
You
open
put it on one side and put it together. Then
yeah, but
pull it out, it would be on both sides, correct? It would stick to both sides, and then it stick again to both sides. You just try and it will work. You will feel it, yeah.
Okay, thank you so much.
Very technical question.
Thank you very much. Simple question, beautiful answer. Sometimes it's about trial and error, right? All right. Next question. Wow. Okay. This gentleman, go ahead.
Hi. Hello, Professor. My name is Jian from Lawrence Ting School, and my question is how to mass produce graphene for commercial purposes.
You're a bit late with this one because it has been produced in tons, many tons, probably hundreds of tons, and in square kilometers already, especially mainland China. There were many, probably too many companies which produce graphene as a powder. There are so many ways of producing graphite. It's low quality. This is why sticky tape is used in academia. But one of those techniques is very simple. You put graphite powder in a container with, say, some kind of oily substance and ultrasound it for an hour. And then spin it, and the thinnest flake will be on the top. You separate thinnest plate, because this is mass production, industrial production, which is used for electric vehicles, for batteries for electric vehicles. It's essentially ultrasound, which breaks your stones into smaller and smaller pieces rather than Scotch tape, but there are many other ways.
Thank you, Professor.
Thank you. So graphene is not just science, it's technology, because there's a lot of real world applications. Thank you. All right, next question. You guys are on fire. All right, please.
Hi, Professor. I'm Emily from Taipei First Girls High School. I would like to know what your biggest challenge non-academically is you've ever faced in life.
Sorry, I was looking at another girl. I missed your question, yeah.
What is the biggest non-academic challenge you've ever faced in life?
What is the hardest academic challenge I have ever faced in life? Yeah. Academic challenge. It's not my one challenge. Okay, let me be personal. One challenge was personal, but working challenge. I would say. I was born and brought in the Soviet Union, and then Soviet Union collapsed. And I'm of the age of 32 with PhD, with no work. I had a work, but I can't do anything useful. So I found a work in the West, in Denmark and in England, as a postdoctoral researcher, first a visitor. So my English is as good as, well, slightly better as an English of a taxi driver in Taipei. And I come to Britain with £1 coin in my pocket. That was kind of a challenge. And more interesting challenge, which is scientifically, presumably, is when we published the first paper about graphene. Okay, it was all kind of problems with publication. It was in Science and twice rejected by Nature and so on, but it kind of expected. But then I went to conferences and presented my results on graphene about the properties of the material, even it was not real single layer at that time, probably 2-3 layers, and people didn't believe me. And friends from old days came around and told me, one of them told me, you know, you should be careful. They thought that I'm presenting a scientific fraud. So unusual it was. Challenge, but a few months later, it was happy end, and someone reproduced those results, and it was plain sailing. Hard work, but plain sailing. Okay.
Thank you. Excuse me. Quite a challenge. Sometimes it's just about charging forward and keep exploring, right? Next, let's see. We haven't heard anyone from this side yet. So, oh yeah, go ahead.
Good morning, everybody. My name is Shweta Jain, and I'm representing Wells International School from Bangkok, Thailand. Professor, my question is a bit theoretical. So far, I have been teaching my students that diamond is the hardest substance known because of its sp3 hybridization and because of its carbon-carbon bond strength. But today, I get to know that graphene is harder than diamond. Can you please explain to me why we should say that graphene is the hardest material around?
This notion that graphene is the strongest and hardest material in the world, it's a common notion in the community. But I think you need to be careful with this notion. So you have to take into account the thickness. If you make a monolayer of diamonds, it would be much weaker, not as stiff, as strong as graphene. And the reason is because graphene bond is shorter than diamond bond, in fact, and arrangement in the bonds. So it's the same carbon-carbon bond, but it's shorter, the bond. This is why it's stronger. It's hard to compare three-dimensional material. The thicker the material, the harder it's break. We know this. The big stick or a thin stick to break. So, but to give you the idea how strong graphene is, it's a single layer, and you can make a membrane of this material which could be a millimeter in size, and you can apply pressure of a couple of bars, or you can poke with your hair or even with a small stick into this one and it doesn't break. Try to do the same trick to polish diamond to sub-micron thickness, and it will be a very weak material, not only because of the bond is weaker, but also because you introduce defects in this material. Another reason why this material exists is not only the strongest bond, but because it's very hard to introduce defects. Those pieces I have shown you, they are perfect crystal lattice. And in order to break material, it's easier to break when there are weak spots already. In diamonds, there are weak spots. In this material, they're monocrystals without weak spots. So it's not a simple one-to-one comparison, but it is correct comparison.
Thank you. I was just wondering about the same thing. Beautiful question. All right, next question. Wow. It's really hard to pick one. Dr. Geim, would you prefer to pick one yourself?
This girl was overlooked over there. I tried to answer.
All right, go ahead.
Thank you, Professor. I'm Wen-Chang from Taipei First Schools and from Taiwan. So my question is there anything or anyone who makes you decided to do research and do research on physics? Thank you.
Say it again. Someone decided to make research?
Is there anything or anyone who makes you decided to do research?
Make me personally in physics. Yeah, I don't know. It's all parents which influence which career and your school. So there is no magic. There is no. There is just observation. Everyone of certain age has, after you go to university, at the age of 30, everyone knows why they have chosen career. First, parents push them in certain direction, either push them as they do in China and in Taiwan, or in my case, it was a personal example. My parents were engineers, so technical people. But more importantly, when you are at school and you have your studies, some people are better than others in art, in I don't know, in literature, and some people are good in math, in other things, and it's kind of a snowball effect. You try if you are discouraged if you find out that, as I am, absolutely horrible is in singing. You try to avoid this subject, and if you are good in math, you try to perfect your skills. So it's snowball effect. You forces your peers, your parents, stimulate to go to where your brain has predisposition. So no magic of that. You will learn it your way when you are 30. Yeah.
Thank you. It's about exploring everything and probably find out what clicks, right? All right.
Like Singaporeans, other Singaporeans, I'm few percent, there were no questions from Singapore, I'm few percent Singaporean. I spent 2 years of my life in Singapore, and I like to have a question from Singapore. In Singlish, please.
All right, questions from Singapore.
Oh, let's tell the story. No questions, okay. Okay.
Hi, I'm Elios from Singapore. Yeah. You mentioned before that you didn't pursue one specific area of research throughout your career, but you decided to hop from topic to topic, right? Do you think that influence, like with the publish and perish culture and research, right? Do you think that influenced how well you did in your career?
Yeah, we live in the world when there is a lot of pressure to be specialized, and there is a lot of pressure not to jump from subject to subject, because yeah, I have had it's such tough time publishing this paper of graphene, as I just mentioned. People didn't believe it. If you're outsider from the community, it's very tough. People use different language. It's still English, but it's completely different way of presenting things. And I have to tell you, it doesn't help to be a Nobel Laureate. Recently, a couple of years ago, we tried to publish a paper on catalysis, where I have no background, but graphene brought news into this area. It was such a tough job because language and the way presenting and what you should present, it's completely different from the communities, not one, but many communities whose languages I learned. So it's tough, and that's way of life. But as at least my example shows, when you break the barrier, eventually and dare to go into the unknown and face those challenges, then it's brings benefits to you, to community, and so on. But make no mistake, it's against human culture, against science culture. Very tough job to re-specialize in another area, even a small step. Tough.
Thank you for the question. So try what resonates with you. It doesn't have to be your specialized field, right? Next question. All right. Let's hear from, all right, that student.
Hello, Professor. I'm Karen from Taipei First Girl High School. And about the experiment of magnetic fields. I want to ask if a human being is capable of floating inside a huge magnet.
Say it again. If human beings can fit in those magnets?
Yeah, can we like float inside a huge magnet?
It's a good question. I thought it was a stupid question. 30 years ago, someone asked me this question, and I thought, what a dumb question. Who wants to put a human inside the magnet? And then frog is okay. And then there were a few volunteers who would like to go inside the magnet. And then, to my surprise, my colleagues from the United States, there is high magnet field facility in Tallahassee, Florida, where they have probably now the strongest magnetic field is in China since last year, but before that it was in US in Tallahassee. They make a calculations what would require to levitate a human. I don't know what they made by human, but probably someone of your size rather than of my size. And to my great surprise, it turned out to be possible. I couldn't believe that. Yeah. They modeled a human, actually, I remember it correctly, as a pig somehow. The size of the pig. Probably it was politically incorrect to put human into there. So they say, okay, let's take a pig, whether we can levitate a pig 70 kilograms in size, and it's possible. It would require the same highest magnetic fields which exist around in those facilities. It would be a big bore. It should be a combination of electromagnet and superconducting magnets. The whole facility would cost in 25, 30 years ago money something like $50 million. But in addition to that, there was a little bit trouble. They need a nuclear power station next to this magnet in order to have enough power through those electromagnets. So the project has never gone live for obvious reasons. Probably most important, not money, but scientifically, because people were talking about training astronauts and something like that. But scientifically, it was not very, very interesting. Okay.
So in theory, it is possible. I thought about doing this morning. I was watching a video about humans levitating. Fascinating. Let's see what happens in the future. All right, next question. Okay, right here, please.
Hello, so I'm Hyon from Wells International School, Thailand. So about your gecko tape model, during class, I learned that geckos climb using the phenomenon of van der Waals, but instead today you told us that they use their hair on their toes since it's dense and compact. So are there any effect of van der Waals in the climbing of geckos?
How van der Waals? What?
The van der Waals phenomenon? Like when the atoms like stick and like, yeah.
Yeah, it's van der Waals phenomenon behind what you want me to answer. I'm sorry.
Oh, sorry. I was just wondering if van der Waals is a factor of geckos being able to climb.
I can't understand what he's saying. Don't worry.
Is van der Waals a factor of geckos being able to climb surfaces?
Yeah.
Okay.
It's correctly. It's van der Waals attraction between different atoms.
Okay.
It's a universal force. Any two materials would be sticking in the same way.
Okay.
You can't avoid it. It's how atoms interact with each other.
Okay, thank you.
Okay.
Thank you. So it's Adam. It works with anything. Next question. Let's see. All right, that gentleman there. Yes, go ahead.
Hi, Professor, and I'm Richard from Advanced Experimental Height, and I'm working on the project. Okay, and I'm heard that the graphene accelerates cell growth in biomatter. I was wondering what your whole purpose was doing for this, and I'm also wondering. I really admire your research. May I take a photo with you if it's not offensive?
I think we forget what the original question was. That's a fan.
The answer is 42.
Could you repeat the question? Thank you.
What your anatomy was doing for this? For doing this? What's your purpose at?
Oh, okay. He's asking about the purpose of your research. Am I right about that? Yeah. Did you have a purpose in mind while doing research on graphene?
Now or before? Originally, there are so many goals in the research. Which one do you? Why did I start it? I explained why I started. Please be more specific. What?
Yeah, the original one.
Original one. The original one. Yeah, I wanted to make graphene as graphite as thin as possible. I never thought it would be down to a single layer. It was unexpected, but the question was, yes, it was written on my slide, how thin you can make graphite. And what properties this material would be, how they would be different from thick pieces of graphite. How you get a chunk of gold, how different its properties from thin film of gold. That was the original question.
This is fascinating because sometimes you have a goal, you want to do something, but you don't necessarily have a purpose. And sometimes that's good enough, right? All right, thank you. Next question. All right. It's getting harder and harder because there's more and more hands right now. Right there, that girl. Yes, please.
Hello. Okay. Hi, Professor. I'm Ray from Yongchen High School, and I have a simple question: Is how do you define a study that is a good study? Even if it is very, very simple, is it still a good study?
She's wondering about your definition of a good study. What is a good study? Yeah.
What is good? What is
What is a good research study?
Yeah, it's a tough one because you never know at the beginning what will be good, what it is bad. Only the road will tell. When you start walking along the road, only at the end of the road of your journey, you can tell whether it was a good journey or not. So as they say in Britain, the proof is in the pudding. So the result matters. So you start maybe with a dumb idea, and it will turn out to be a dumb result, which you rather forget. But sometimes you start, even with a very bad idea, you start moving randomly from one doing something, it forces to make you another step and then another step and then another, and it brings you to something interesting worth studying. So, but the original idea, this sounded very, very simple, but sometimes the original idea could be very wrong. But then you walk along the way, you do experiments, you start doing things, and then that's it. It brings you to some interesting results.
All right, so the answer is you don't know.
Yeah.
Just do it like Steve Jobs says. It's only when you look back that you can connect the dots and know whether or not it was a good study. All right, we have about 5 more minutes. Let's take 1 or 2 more questions. Let's see, next question. Oh gosh. All right. Oh yeah. Okay. Japanese students. Ujira. Okay, go ahead.
I'm from Japan, Tennoji High School. You told us a lot about the characteristic of graphene, but what was the most interesting or mysterious feature?
What most interesting in?
You told us a lot about the...
No, it was very good English, but what was the most interesting and mysterious feature? Well, I tried to answer this question in my talk. It depends on who you are talking. Many people, thousands and thousands of researchers around the world work on graphene and similar materials, and they have their favorites. For me, probably the most unusual feature was that this material exists. And I think this is the most exciting feature, that despite all this vibration, despite air, despite water, despite oxygen, this material still exists, and you can poke in this material even probably with your finger. That's most exciting, but I think the most exciting feature for the Nobel Prize Committee was its electronic properties of graphene. People say it's the most conductive material, and so on. But one, I didn't touch it because it's too specialized subject. But let me give you an idea. So electrons within graphene allows us to mimic the phenomena which people was trying to find for 100 years using accelerators like CERN accelerator. Some phenomena couldn't be observed in the most powerful accelerators particle physicists built, and those phenomena have been seen in graphene on the basis of how electrons behave. They mimic those phenomena which predicted based on Einstein kind of physics. And that was excited the scientific community, not the gadgets, but not electric vehicles can be doing this, but a physics, relativistic Einstein kind of physics being studied with the help of graphene.
Thank you. I don't know if you heard that key word that Dr. Geim said one over and over again, exciting. So follow what excites you, and follow something that makes you forget time. Next question, maybe final question. All right. All right, there in the middle. Go ahead.
Good morning, Professor Geim. I am Paula from Taipei First Girls High School, and I have 2 simple questions for you. The first one is that you just mentioned that it's already possible for human beings to levitate, and you said that your colleagues might like to, but I'm curious about will you like to be levitated? The second question is that it's out of my curiosity. After you discovered the way of creating the graphene, what other projects or experiments are you working on right now? Or what would you like to work on in your future? Thank you.
I got the second question. Okay, yeah, I missed the first one. So let me answer the second question. You, you know, people ask, "Oh, you like to change your research area? You didn't change it for the last 15 years," and the reason is that we have found, I did change it actually several times over the last 15 years, jumping into completely different disciplines. We start studying how protons behave, we start studying properties of low-dimensional water, but graphene and other thin materials get a new kind of tools. We have a new toolbox. Previously, you know, scientists had in their toolbox pliers, whatever, gold wires, metal wires, thin films of different. Now we have a whole library of graphene and graphene-like materials, and this allows us to construct experiments on atomically thin level. For example, what I called graphene 3.0 is so-called van der Waals heterostructures. When you take graphene or similar materials and put them on top of each other and try to make a three-dimensional material with new kind of properties. That's, for me, was exciting for the last 10 years. Very recently, we also studied properties of water. When you squeeze, using this graphene as a tool, not a subject of study, we can squeeze water to 1, 2, 3 layers and study how it behaves. And for example, a paper published just a few weeks ago in Nature is about properties of this water. Water becomes becomes kind of million times more conductive when it's squeezed to this earth, and it becomes ferroelectric, which is, you don't expect this at this scale. And at the same time, it's very important because this thin layer of water everywhere around us. So that's kind of thing excites me. On one hand, it's very graphene related because it's atomically thin. On the other hand, it's way away from my previous area of expertise and nothing to have to do with graphene per se.
Thank you, Professor. Thank you for your insights. And the first question is, do you want to be levitated? I believe. All right. I want you to know how difficult this job is for me to pick a person to answer questions because there's so many hands. But I just want to thank you, Professor Geim, once again for sharing your insights, your time, and your journey with us. And to everyone in the audience, I hope you understand through today's conversation that science is not just about experiments, equations, or formulas. It's about curiosity, creativity, and the courage to keep exploring. So keep learning, keep exploring, and stay hungry and stay curious. Thank you, everyone. A big round of applause for Dr. Geim again.
Thank you, guys. It was a pleasure being here. Thank you.
Thank you, Teacher Bryant. We would like to invite Professor Geim to the stage. We have prepared a special gift for you. The gift is a Japanese character, Chibi Maruko-chan, wearing our green uniform. This doll has become a traditional gift to every Nobel laureate who visited our school, and it's a limited edition. Thank you.
Thank you everyone for being so engaged. We will now take a short break until 11:15.